Okay. All right, it was meant to be a short break. The hardest part about a break is coming back, no matter what kind of break it is or when you take it. It's like to get people back from the break. Well, good. I'm glad that you took the opportunity there to visit with one another. That's very good. It's always nice to hear that chatter of people in a room. It's wonderful to hear that again. So very happy for that. All right, we're going to continue on. Our next speaker, Mr. Robert Legg. Robert Legg is the director of the Petroleum Products Research Department in the Fuels and Lubricants Research Division. In his over 34 years at SwRI, he has served as the department's quality control representative and fuels laboratory manager prior to becoming department director. He has been involved in all aspects of laboratories testing, from routine testing to method development and quality control of testing processes. Robert is currently serving as the chair of ASTM Subcommittee on Combustion Characteristics and remains involved in both national and international octane, cetane, and constant volume combustion chamber method development working groups. He is also well-versed in the United States federal regulations as they apply to the collection and testing of field samples for compliance purposes. Robert was born in Huntingdonshire, England. Robert's family moved to San Antonio when he was fairly young, so we'll consider him a South Texan. Robert earned his BS in physics from the University of Texas here in San Antonio. 3 things you might not know about Robert. He has a background in theater arts. In fact, he started to pursue a degree in theater arts after graduation from high school. He used to be a puppeteer, believe it or not. And he likes taking photographs, particularly landscape and architectural photography. Are we good to go? We got him up? Okay. Please give a warm Tom Talks welcome to Robert Legg.
Thank you, Tony. Before I started working at Southwest Research Institute, I really never gave much thought to the fuel that I put in my vehicle. I usually just followed the family tradition of using the same fuel that my father put in the family van. His choice of fuel was usually based on a previously bad experience. It wouldn't be uncommon for me to hear, "I'll never put so high of fuel in the car because the last time I did, the van never ran properly." Or my choice of fuel was based upon marketing. I mean, who wouldn't want to trust their car to the man who wears a star? Or who wouldn't want to put a tiger in their tank? I know those references are probably dating me. But after I began working in the Fuels and Lubricants Department, I began to gain a deeper understanding of what goes into the processes behind making fuel and distributing fuel. I also learned what was important to that fuel in order for it to perform properly as intended in the vehicle. So this evening, I hope to sort of share some of the knowledge that I've gained and hope you'll come away with a better understanding of what it takes to make that gallon of gasoline, what it takes to get that gallon of gasoline to the gas station, and truly the importance of a quality oversight program. So prior to the advent of the automobile, gasoline was an unwanted and somewhat byproduct of the refining industry. You see, back in the day when they first started refining, the main thing they were after was illuminating oil or kerosene for the lamps. Sometimes this unwanted product we call gasoline today, they just sort of release it into the local waterways under the cover of darkness. This was well before the establishment of the EPA. However, with the automobile, that changed. Now they had a ready market for this unwanted byproduct. Now, the early gasoline was particularly bad. Some of the octane numbers were on the order of 25. But not to worry, those early automobiles were not very discriminating either. But over the years, as the number of cars on the road became more and more the need or the thirst for gasoline significantly increased. So they had to find ways to make more gasoline out of a barrel of oil. So one of the first processes they developed was a thermal cracking process. What this essentially does is it takes those heavier, larger molecules in the gasoline, more in the lubrication range, and they break them down to smaller molecules that are more applicable to the internal combustion engine. But even still, as more and more cars developed on the road, there were still not enough from this process. So they ended up developing more and more processes, such as the alkylation process, the isomerization process, and the reformation process. So we end up going from this, what you see up here in the right-hand corner is a single batch process distillery or a refinery, to the more complex modern refinery. Natural gasoline that comes from a barrel of oil, you only get about 15 to 17 gallons out of that barrel. Through these upgrading processes, the refiners were now able to develop about 20 to 22 gallons of gasoline from a typical 42-gallon barrel of oil. Now, some of these processes, like the isomerization, they make molecules that are perfectly suited for the internal combustion engine. Some of the other processes, like the catalytic cracking unit and any of the other units that break apart the molecules, sometimes create more undesirable products that can lead to gum formation or early degradation or oxidation of the fuel. So it's very important that these refiners control these products so that none of these undesirable products get into the final fuel that's sold. Now, they usually do a really good job of this, but unfortunately, once the gasoline leaves the refinery, a lot of times they'll lose control over it. So in the United States, according to the Energy Information Agency, we used about 135 billion gallons of gasoline in 2021. To put that in perspective, that gasoline would fit into a box that's about half a mile long, half a mile deep, and half a mile high. That's a lot of gasoline. It'll take 17 million tanker trucks to deliver that gasoline to the 145,000 retail outlets that are in the U.S. alone. If you do the math, that averages out to about 3 deliveries, a delivery every 3 days to each of these gas stations. Now, if you take, for instance, Buc-ee's up there in New Braunfels, that has 120 fueling positions and can store almost 250,000 gallons of fuel, they get quite a bit more than every 3 days. They get more along the lines of 1 delivery about 3 deliveries a day. So if you thought about it, and all those 17 million truckloads delivering fuel from a refinery to the retail gas station, our highways would be clogged with these tanker trucks. So fortunately, most of the fuel is delivered via a common carrier pipeline. This graphic represents all the finished product pipelines across the U.S. This alleviates the need to have those 17 million trucks on the road. Now, the refiner will put it in the pipeline, and it'll end up to a local terminal near and where the fuel is being distributed. San Antonio, we're served by 8 terminals, most of them on the east side, and the pipelines come in from refineries in Corpus Christi, refineries in Three Rivers, and refineries in the Houston-Beaumont area. One thing that most people don't realize is that when you go to ExxonMobil to buy your gas, it's very likely that Exxon did not make that gasoline. It still has to meet their high quality standards, but generally it was made by a different refiner. Now, because these things are because the fuel is carried on a common carrier pipeline, it's known as a fungible product. That's just a fancy way of saying that the products are interchangeable. A refiner may put 70,000 barrels in on the East Coast, and as it travels down the pipeline to the Gulf Coast when they take delivery, product will have been added and product will have been taken away out of that pipeline. So what they take delivery of in the end is not the same product that they made when it left the refinery, hence them losing control. So just think about the way this works. I make a barrel of gasoline, I put it in a pipeline, somebody takes some out, somebody puts some in, some goes to the tank for a while, goes back in the pipeline, finally gets to the local terminal, then it gets put into a truck which has had who knows what in it before. Yes, switch loading still occurs. And it gets delivered to the station where you're going to put in your fuel in your vehicle, and you may or may not know what's been in the tank before. So there's all sorts of potential problems in having fuel quality suffering during the distribution process. And basically that's where we come in. We have developed a network of contractors across the United States that can sample virtually any retail gasoline outlet. We ship out sample kits to these contractors. So far this year, we've shipped out about 7,000 of these kits. Some of the kits go to the terminals, but most of them go to the contractors. They'll take these kits to the fuel station, go to the pumps that people use to fill their cars, and take that same exact fuel. So we're a representative sample of what's being put into the customer tanks. The samples that go to the terminals, our contractors don't go onto the terminals to sample the tanks. We rely on the contractors to pull tank samples, and the contractors will go pick them up and then ship them back to us. So far this year, we've received about 28,000 samples. Now, these contractors can also pick up other samples depending on what our client needs are. They've picked up oils, DEFs, and other products just to help look at quality processes. Now, when we get these samples, you may be asking, what do you do with them? Well, we basically run ASTM standardized tests. We'll provide the data to the clients so that they can assess the quality of the fuel that's in the marketplace, and they'll also use this data to demonstrate compliance with regulatory standards. One of the tests we do, one that everyone here is familiar with, is octane testing. Tony mentioned I'm the chair of this committee, so I know a lot about octane testing. The octane number is basically the resistance of the fuel to knock. Now, this is an extrinsic property of fuel, which means it's very much dependent upon what the engine it's used in. So that's why it's very important that the fuel you put in your vehicle is the one recommended by the vehicle manufacturer. If you use too low of an octane number, it could cause performance problems, and in worst case scenarios, it can cause engine damage. If you put too high of octane in your fuel, in your engine, you're basically just throwing your money away. Now, the next time you go put gasoline in your car, I want you to take a look at the little button, look at the pump. You'll see a number on there, a little equation, R plus M over 2. The octane number actually comes from two tests. The research octane number, which is the RON, and the motor octane number, which is the MON. The average of these two tests result in the AKI, or the anti-knock index, which is how we grade our fuel. So in addition to the different grades of octane, fuel is also seasonal. There's about 9 different volatility grades of gasoline. The fuel you buy in the summer is definitely different than the fuel you buy in the winter. We determine what the volatility grades are based upon 2 tests, the vapor pressure and the vapor-liquid ratio test. Now, if you need a vapor pressure of the fuel that's high enough to aid in the ease of starting of the vehicle, but if your vapor pressure is too high, it can cause vapor lock and your car will not start. Also, too high of a vapor pressure can result in excessive evaporative emissions. This is one of the reasons why the federal and state governments regulate this property. Now, you may have seen in the news where San Antonio is considered marginal non-attainment for ozone action, and the EPA is probably more than likely going to move us into that moderate category. One of the things that may occur with this is that they will lower the maximum amount of vapor pressure that can be sold in this area, which in effect will probably result in higher fuel prices. Another cool test that we do that's related to volatility is distillation. In this test, we actually take the gasoline and we boil it. Now, we have specialized apparatus to do that, so we can do it safely. Yeah. And I don't recommend you try this at home, but you can find some YouTube videos where people do it. Don't try it. What we're looking at is the percentage of the fuel that evaporates at a given temperature. So that 0 to 10% of fuel needs to evaporate enough so that when it volatilizes in the engine, gets in the combustion chamber, the car starts easily under most conditions. The 50% point, looking at that to aid in the drivability of the vehicle, as well as the idling quality. The other one we're looking at is the 90 to final boiling point. In the heavier range of the gasoline, you want it to be low enough that all the fuel will volatilize and all of the fuel will burn in the combustion chamber. If the fuel does not burn, the liquid will seep down past the rings, get into the oil, then you'll have high fuel dilution in the oil, which can lead to a whole host of other problems. One of the other common tests that we run is looking at the oxygenates. You've heard about the ethanol fuel. The ethanol content fuel right now ranges from about 10 to 15%. If the ethanol content is too high, you could also have vehicle performance issues. In addition to that, there are materials compatibility issues. If the car is not specifically designed to handle E85 or flex fuel, it can wreak all sorts of havoc on the car if you put it in your tank. Now, I mentioned earlier that a lot of times that the fuel you buy is not made by the brand that you buy it from. The one thing that the brands do control fairly heavily is the additive packs that they put in the fuel. It'll go to a second-party terminal, but Exxon's additive goes in that Exxon gallon. Valero's additive goes in that Valero gallon. They do control this very tightly. So every gallon of gasoline that's sold in the United States must have a detergent additive in it to meet a minimum performance standard. Many of the refiners subscribe to the top tier program, which means that they use a higher level of additive, more effective additives to provide better performance in the vehicle. Now, one of the ways they make sure that their fuel is being additized properly is they'll mark their fuel with a special molecule. These compounds are not easily detected, they're not easily removed from the gasoline, and they're also fairly unique. They are definitely different than any other molecule in the gasoline. So we've developed special tests, most of them are proprietary tests, to be able to determine the amount of these markers in the gasoline. Now, the markers in the additive pack in a certain percentage, so if knowing how much additive is in or markers in the final product, they can determine and make sure that the product was additized properly. If it's not additized properly, they may not be meeting either the top tier specification or the federal specification for having the least amount of additive concentration in the fuel. So I know you're looking at this and seeing there's all sorts of potential for problems to happen all the way. They could either have a bad fuel that they match, it could get contaminated along the way, who knows what could have happened to that product as it's delivered to the gas station. So you're probably thinking to yourself, you've probably seen all sorts of problems out there. Well, surprisingly, no. Most of the products that we see in the marketplace today, from the samples we collect, meet the minimum specifications. They're usually very good. Now, occasionally we do run across a problem, too much ethanol, not enough octane. But when these are pointed out to the refiners, they usually take swift action to mitigate the problem, so they keep their customers satisfied and they prevent any sort of regulatory violations. So as long as you stick with a branded station and that station is moderately busy and you do not fill up your car when you see a tanker truck there offloading product into the tank, I think it's safe to say that you can trust your car to the man who wears a star, and you can have faith that the quality of the product that you're putting in your tank meets the needs of that vehicle. Thank you.
Nicely done. Thank you, Robert. Tom Slick right there. 75 years we've been around. So, Tom, how much was gas back when you started SwRI? I have that answer. No. So when you attend retirements and things like that around here, they typically go back to when a person first started and give you some facts about that particular year. Well, 75 years ago, 1947, the Institute was started. I have some facts. You want to hear them? Who was president in 1947? Harry Truman. In his first term, who was his vice president? What? What? It's a test question. He didn't have a vice president his first term. I didn't know that till I looked it up. Did you know that? He didn't have a vice president his first term. He took over for when FDR passed. But then Alvin Barkley was his vice president from 49 to 53. Did you also know that Truman was one of the few presidents not to have a college degree? Didn't have a college degree. Of course, Robert's a history buff, so he's going, yeah, I knew that. Yeah, I knew that. Britain's Princess Elizabeth married Philip Mountbatten, Duke of Edinburgh. He was born into Greek and Danish royal families. I didn't know that. I thought he was German. But no, he was from Greek and Danish royal families. The first airplane broke the sound barrier in 47. Who was flying it? Ooh, we knew that one. Chuck Yeager. The transistor was invented in Bell Laboratories in 1947. What do you think the cost of a loaf of bread was? 13 cents. Very good. How about a gallon of gas? 23 cents. 23 cents. And the quality of it was horrible, as we've learned. Also, some prominent people that were born in 1947. Hillary Clinton, David Bowie, Elton John, and Arnold Schwarzenegger. Some of them were politicians. All of them were entertainers, for sure. All right. Our final talk this evening is from Dr. Tracy Becker. Dr. Becker is a planetary scientist and group leader for the Remote Sensing Observers Group of the Planetary Science Section at Southwest Research Institute. She specializes in spacecraft observations of solar systems objects at ultraviolet wavelengths. Her current focus is the study of asteroids and Jupiter's moons using UV observations from the Hubble Space Telescope. She also studies Saturn's rings using UV stellar occultation observations from the Cassini spacecraft and models the shapes of near-Earth asteroids through radar observations conducted at the Arecibo Observatory in Puerto Rico. I got the nod for that. She served as the co-chair for the Composition Working Group for NASA's Europa Clipper mission and is a co-investigator for that mission's ultraviolet spectrograph. She is an affiliate member of the JUICE UVS instrument for the European Space Agency's JUICE mission. Tracy is actively involved in outreach and community service. She has orchestrated numerous hands-on science events for students and professional training courses for teachers. She is the co-founder for the San Antonio Astronomy on Tap public science events and regularly gives talks to local students and to students across the country using the Skype Science program. Originally from Freehold, New Jersey, Tracy earned her BS in astrophysics from Lehigh University and her PhD in physics from the University of Central Florida. 3 things you might not know about Tracy. She is a true crime documentary and podcast enthusiast. She has lived and worked at observatories in Chile and in Puerto Rico. That sounds cool. And she is a newish mom to a very happy 14-month-old named Theo. Please give a warm Tom Talks welcome to Dr. Tracy Becker.
I was going to try to walk, but that's okay. All right, and I'm going to put the clock on here because otherwise I might end up talking about this topic all night. So, hi everyone. Thank you so much for having me, and I'm very happy to be here to round out this excellent session of Tom Talks tonight. And what I'm going to talk a little bit about is how we use ultraviolet to study objects in our solar system, and I'll take you on a brief tour to some of the really cool objects that we have seen using UV instruments built right here at the Southwest Research Institute. So first, before I take you on that tour, we're going to go to a warm, sunny beach. Hopefully, like I have to do, most of you maybe the first thing you do when you get to a nice warm place like this, I know we were already talking about getting into the fall and enjoying the cool weather, But I enjoy the beach, and I always have to do sunscreen, right, first. And that's because what most of us associate ultraviolet light with is the type of light that burns our skin. That is what a lot of us usually think of with ultraviolet light. But actually, most of that UV light does not end up reaching the surface of the Earth. Most of that is blocked by the atmosphere, which is fantastic for our skin and terrible for ultraviolet science of the solar system. And so if we want to study objects that reflect light or emit light at ultraviolet wavelengths, we have to get up and above the atmosphere. We have to go into space. That's one of the cool things we do here at Southwest Research Institute. So what am I talking about looking in the UV? So if you remember the days of using a prism and shining a white light through that prism and seeing the colors that come out of it, the whole spectrum of the rainbow, you can see that here behind me. But that's only a small portion of the entire electromagnetic spectrum. When you look at the entire thing, it's much broader than that. And actually, the visible light is just a small portion of the entire spectrum. What we're going to focus on here is the ultraviolet light. So why? Why do we care about the ultraviolet light? Why do we care about the visible light? Well, one of the really cool things about the electromagnetic spectrum is the way it interacts with matter. And so if you have a material that's reflecting light, or in this case, what I'm going to show here, a cloud that could be absorbing or emitting light, it's going to interact with the light that comes onto it very specifically based on its composition. So the atoms or the molecules will absorb light or emit light at very specific energies or frequencies, or what we often refer to as wavelengths of light. And so if you have the prism with nothing blocking it, you get this nice, beautiful rainbow of colors. But if the source of light ends up interacting with a gas, it may absorb, the electrons may absorb some of that energy. And if you remember maybe some of these orbital diagrams of an electron, of an atom, the electron could get that energy, move up in an orbital shell, and actually end up taking away some of that energy, and you end up with these little gaps in that beautiful spectrum. If instead the atom actually releases some energy, you may get emission lines. But the key here is that those lines are happening at very specific energies related to the composition of the material, the type of atom. If it's an oxygen or a hydrogen atom, it's going to look differently. This pattern will look different. And therefore, these signatures are essentially the fingerprints of materials that we study in the universe. And so it's a space talk. Here's a fancy picture. You might be asking, what kinds of clouds do we see in space? Well, this is actually one of those types of clouds. This is a star-forming region. This is one of the first images taken by the JWST, the James Webb Space Telescope. And this is an infrared instrument. So this is all not really visible light. And our JWST, our Hubble, they don't have flashes on their cameras, right? We're not taking an image by flashing out into space and getting what's reflected back. We're interpreting these colors and these compositions based on the way we see these molecules and these atoms in these clouds interact with light. We also can see emission from different events happening in space. So this is actually the aurora, or the northern lights, essentially, of Jupiter. These are some images taken from the Hubble Space Telescope. And this is where light is actually being emitted from the atoms and molecules that are getting excited at the pole of Jupiter, partly because Jupiter has a crazy magnetic field, and it really pulls in some of those solar photons and interacts with the material that make up the atmosphere. And again, the way it interacts, the way we see these lights shine, tells us what is actually being interacted with, what kinds of molecules or atoms are there. And so you could imagine if you had that prism, this is actually what the solar spectrum looks like in that prism, because the sun has gases, it has different material in it. It has hydrogen and helium mostly, but it has actually a plethora of different types of atoms and molecules in it. And so as scientists, we take a really pretty picture like this and we turn it into a squiggly line, because that's what we do. But what you can see is all these little bite outs represent some sort of those fingerprints of the material that's there. And you can see that same type of bite outs sort of in these little wiggles of this line. And you can see that the maximum signal for the solar spectrum is right here in these visible color wavelengths. Not surprising that our eyes have adapted to be interested in those colors. So one of the other things we can do is say, okay, here's our squiggly line just in the ultraviolet. What does the sun look like at just one of these wavelengths? Well, at that one, it looks like this. But at this other one, it looks like this. So you can see the differences that we can actually learn about the sun. You can see some of the material that's sort of on the sides out here that you don't see in this image. There's different structure we see at that image than the other image. So you can do this at a bunch of different wavelengths and compare them, and you can learn different things by studying objects at different wavelengths of light. Similarly with reflected light, this is an image of Jupiter. Most of us are familiar with the visible image, but in the UV, the ultraviolet, and in the infrared, it looks different. So the key thing I want you to know from all this rambling about all this different wavelength, energy, light, the key takeaway is that we can learn unique information by studying different objects at different wavelengths of light. Okay, so now what do we do with that? Well, we've done some really cool things with that. So here at the Southwest Research Institute, we build some of the greatest ultraviolet instruments that have flown through the solar system. This is just a family tree of the UVS family, the UV spectrographs that we build here. Here are just a few, and here are just also some actual pictures of them. I've seen a lot of people in the audience. How many of you here have actually worked on one of these UV instruments in some way? Sandy, raise your hand. All of you, lots of people, yeah. Awesome. So many people, and this is just a few. There are tons and tons of engineers that work on these, and the scientists who then use them to study space. So what have we actually done with some of these? Well, first, it turns out, I learned this only a few years ago, that we've actually had a long history of UV exploration. The first UV instrument developed at Southwest Research was done using the IR&D program here. And it flew multiple times on suborbital spacecraft, but also went on to the shuttle, and not only on a couple different shuttle flights, but one of them was commanded by Eileen Collins, who now serves on our board, so it's kind of comes full circle. Since then, we've had that family of UV instruments that I showed a few slides ago, and one of the first really cool places it went was to a comet. This is comet 67P, Churyumov-Gerasimenko. You heard me go to observatories in South America and Central America. I do not speak Russian, so that was my attempt at that name. But this is a comet that we flew a spacecraft to. It was very cool because we caught up with this comet, and we were able to see when the sublimation started to take place. So comets make these beautiful tails, but when does the water come off? When does the carbon dioxide come off? When do all the materials start to sublimate and form that beautiful tail? And these tails are some of the material that actually infall to Earth as shooting stars or meteor showers as we see them. So we need to know a little bit more about these materials. They're also pristine from the far reaches of our solar system. So we also learn a little bit about the initial stuff that made up the solar system and made up who we are, what the Earth is, and everything around us. So the UV instrument is sensitive, again, to some of those spectral signatures that we see. And in particular, for this case, it was looking at the rate of production of water and of carbon monoxide and carbon dioxide. You may have heard that we flew past Pluto a few years ago. Yes? Yeah? So with the New Horizons spacecraft, the UV instrument on board studied Pluto's atmosphere, did an occultation. They studied the composition of Pluto's surface and its moon Charon's surface, as well as the Kuiper Belt object Arrokoth that it recently flew by. Some of that surface study we're actually replicating in the lab here at Southwest Research right now, so we're learning more about what that composition is based on the UV observations. And now that it's out just kind of far out in the solar system, it's still doing science, this UV instrument, as well as all of the other instruments on the New Horizons mission, studying things like the hydrogen wall at the edge of the solar system. And this is something only the Voyager spacecrafts were able to see because we don't have that many spacecrafts operating that far out into space. The Lyman Alpha Mapping Project is on a mission that is currently orbiting the moon. And so this is actually mapping the water on the moon, particularly the water that gets trapped in some cold spots known as permanently shadowed regions. These are kind of deeper craters towards the poles where the sun doesn't shine. But we see the light using starlight. The ambient starlight actually shines the light that we can use to then see if there's actually water there or not. The Juno mission, have you heard of it? Yes, okay. Also run here out of Southwest Research Institute. The UV instrument on board there is mapping some of the aurora, again, those northern lights of Jupiter. You can see that image here. This is sort of a false color one here. This one you can see, oops, sorry, I'm pointing in the wrong place. You can't see that. This is false color. But here, oh, they're all false color because it's ultraviolet. But you can see actually some of these little features that are actually showing you where the moon's interaction with the magnetic field of Jupiter is basically manifested in some of these cool little dots. These are the footprints of the moons. And now Juno is actually flying by the moons, which is extra cool. Future missions, so those are all the ones in existence. Right now, the JUICE UVS is a European Space Agency mission, is JUICE. It's going to go into the Jupiter system. We built and delivered the UV instrument that will fly on board that mission. It's going to study the atmosphere of Jupiter. It's going to understand the whole system around Jupiter. There are Jupiter's moon Io actually spews sulfur through its volcanoes, and how does that interact with the magnetic field and the other moons? We're going to find that out using our UV instrument as well as the other instruments on board. And it's going to specifically study the moon Ganymede, which is it's the only moon in the solar system to have its own magnetic field. And so it produces these aurora pretty regularly that I've already hopefully convinced you the UV is great at studying. And last, I won't say I saved the best for last, but maybe I'm biased because this is the one I work on. But Europa Clipper is NASA's next really big mission, and it's going to the moon Europa. It's one of Jupiter's large moons. And the reason it's going there is that this moon has an icy shell with a liquid water ocean underneath. It has more liquid water there than in all of Earth's oceans combined, times 2. So there's a lot of water. So when you think of water in space, what do you think of next? Life, very good. So the Europa Clipper mission is going to head to this moon to study the habitability of that moon. It will not necessarily say whether life is there or not, but it will say if the conditions there are sufficient, if the temperature of the ocean, the salinity of the ocean is sufficient for life as we sort of understand it right now. The UV instrument on board is going to do a couple of really cool things. First, the first detection of possible water plumes, aka geysers or water volcanoes, coming out of Europa were detected using a UV instrument on the Hubble Space Telescope by scientists right here at the Southwest Research Institute, including Dr. Kurt Rutherford, who's in the audience. These were detected by looking at those auroral emissions coming out of the signature of hydrogen-oxygen at the exact right ratio to indicate that they were basically water molecules being dissociated as they came out through a possible eruption. So the UV instrument on board is the plume hunter. It will look for those plumes. It will analyze those plumes if we see them. It will also just study the atmosphere and the surface composition of the moon and do just other really cool science while we're there. Lastly, I just want to end by saying that these projects kind of demonstrate the core strength of the Southwest Research Institute. This is an opportunity for engineers and the scientists to work directly together, hand in hand, to build these fantastic instruments and do the cool space exploration that we're doing. The UV instrument that I just showed was already built and delivered to NASA's Jet Propulsion Lab earlier this year. So it's the most recent UV instrument that's been built here, but certainly not the last. So I look forward to a long future of studying space objects, solar system objects in the ultraviolet using SwRI instruments. Thank you.
Thank you, Tracy. That was fantastic. I really feel like we need some space science theme music. We need Star Trek or something. Should be playing in the background for those cool things that we do. Well, that concludes our talks for this evening. We do Tom Talks twice a year in April and October. And this space up here it needs you on it. You do some